Hello everyone. Nice to meet you, and it is a great honor to speak at the OpenSearch conference. This is actually my first conference about the OpenSearch. And my name is Hello Lee, and today my topic is managing over 1,000 OpenSearch clusters in a private cloud. I'm from South Korea, and I work as a cloud service engineer at a messaging platform company called Line. My presentation will consist of three main parts. The first, I will introduce how we operate OpenSearch in our private cloud environment, focusing especially on our service architecture. In particular, I will highlight our node structure that uses lightweight network storage and share what benefits we achieved by adapting these storage architectures. And second and third parts, I will cover two real-world storage issues we experienced with while operating OpenSearch. And I believe our experience will help to other people to considering applying the network storage on the OpenSearch. Before starting the main presentation, I'd like to briefly introduce myself. As mentioned earlier, I'm currently working as a cloud service engineer at Line. Line is a messaging platform widely used in Asia, especially popular in Japan. And besides messaging, we provide various other services such as music, comics, and shopping, and many other products we have. And I've been responsible for developing and operating OpenSearch as a service at Line for about 5 years. Now I'd like to introduce our service architecture. Before we move on, let me briefly explain why we operate private cloud. There is three main reasons we run private cloud. The first one is the security and data protection. We have various user data as a messenger-based platform, so it requires higher-level data security, and sometimes we need to make our own tools for protect our data. And the second reason is cost efficiency. To operating large-scale services on the public cloud, it is very it takes a lot of cost. So run private cloud, it is the chance to reduce some costs. And the last reason is flexibility of the features. When a particular line services requires a specific feature on the cloud, our cloud team can support quickly. So I think that is one of the benefits to run private cloud. Now let's talk about the OpenSearch. Currently, we have over 1,200 clusters in this private cloud environment. And these clusters stores more than 6 petabytes of data, and we have 2 regions in Japan. So these clusters used for many purposes like log storage, data analysis, and monitoring, and also the search engines. Now, let me introduce our OpenSearch service, especially highlighting how we use network storage. First, let me show our service architecture. As you can see, we have set up controllers and API servers and monitoring pipelines on the Kubernetes. However, the OpenSearch nodes themselves use OpenStack-based virtual machine and storage services, not on the Kubernetes. You might wonder why not just run OpenSearch directly on Kubernetes. As you know, the OpenSearch officially supports a Kubernetes operator to install and run OpenSearch clusters on the Kubernetes clusters. And Kubernetes it has advantages of maintaining service and provides useful feature to operate service on there. But there is potential issues with the control plane fails can affect all the OpenSearch clusters. For example, let me tell the incident with the ChatGPT last December. This service outages shut down entire ChatGPT service over 4 hours, and it was due to Kubernetes API server overload. And we also experienced similar service disruption started from Kubernetes in few times. So based on this experience, we involved our service architecture to ensure separation between control plane issues control plane issues affect to the OpenSearch functionalities. So now with these separated architectures, we can protect even the control plane fails. So that's why we choose VM-based architectures. And next, let's discuss about the network storage. As many of you know, OpenSearch installation guide does not recommend use network storage. That's because the performance issues. Initially, we also followed this guideline. We also operate our dedicated servers with the large-scale solid-state drives to run OpenSearch. However, the operating dedicated server is very hassle, and the node affinity issues can arise when building large clusters. And also, the data tiering is one of the burden to run on the dedicated servers. As our service grows, some users want more performance for their search engines, and at the same time, other users want to bigger OpenSearch node to store their logs. So we transitioned from local storage to the network storage for more flexible resource allocation and the efficient storage operations. For high-performance nodes, we adapted NVMe over Fabric storage for our hot-type nodes. The NVMe over Fabric is a network protocol that connects NVMe disk through the network. And so we can configure NVMe over Fabric disk with RAID configuration for data protection and reliabilities. So this type of storage have advantages. It offers high performance because NVMe disk is very fast than the other types of storage. But this structure introduced redundant data replication with OpenSearch's own data replication policies. So in these diagrams, if we store some data, OpenSearch replicates to one or more by the number of replica settings, and then the NVMe disk copy once again by the RAID configuration. So that is redundant, and this is amplifying the disadvantages. So to solve this, we introduced a lightweight storages. We called it the NVMe Lite. It uses a single NVMe disk without any replication strategies. So the advantage of this structure is very clear. The storage cost and network cost are reduced as half than the RAID 1 configuration. So we can save money to operate OpenSearch, but disadvantage is data may be lost if this fails. So that is very critical point of the network storage. However, we have ensured data fault tolerance in the OpenSearch with the multi-zone shard affinity and shard replication settings in OpenSearch. So we relies on the OpenSearch only, not from the network storage. So it allows more resources for the search performance, such as we use more replica, and then we have 3 shards, but we only use 3 of an NVMe disk. So we have more search performance with a reduced cost. So let me show our migration case. This large-scale migration involved moving 6.1 petabytes of data into our OpenSearch service. So we applied hard-on architecture, and then we plan to store 2.0 petabytes of data to hot type nodes. It means NVMe attached virtual machines. And after applying this lightweight storage, the project cost of this migration case were reduced by 22%. It is difficult to specify exact saving because there are some kind of contract issues. You can imagine how many servers would typically be needed to store 6 petabytes of data. Then 22% is quite big. Yeah. Now let's move on to the case study. By using the network storage with OpenSearch, it improved our cost efficiency and also data safety for the cold tier nodes. But however, we also encountered some issues along the way. So let me share one major case is the checksum failed issues. Maybe some of you see that errors on your OpenSearch clusters. The checksum failed error is occurred when read data from the stored shard, and suddenly the checksum failed errors occurs, and the shard turned to unassigned status. It means that OpenSearch failed test of the checksum on the specific shard, and OpenSearch determined this data is invalid. And this issue occurs in only cold tier nodes. The cold tier node means that the block storage attached block storage volumes, and it does not occur in hot tier nodes. It using NVMe disk that I mentioned earlier. And when this happens, OpenSearch can recover itself using the replica shard. So initially, this issue might seem critical because OpenSearch can recover itself without any operations. But after some investigations, we identified 2 serious concerns from that. The first one is this issue can be discovered during read operation, not write. So making it hard to determine when the problem started. Yeah, when we write some data, the error not occurs, and after maybe some days or some month, when we try to read data or OpenSearch try to move shard from one node from the others, this errors has been occurred. The second reason is more fundamental issue, I think. The primary and the replica shard contains different data. If one of shards in the pair of the primary and replica, it has been corrupted, OpenSearch can recover itself using the other shards, then it means that one of shards failed to check some test, but the other one is passed. So it means that the primary and replica shard has different data, and it stores a very long time until the error occurs on one side. So we treated this as a very serious issue. So to identify the cause, we conducted extensive testing on possible factors, including OpenSearch versions and Lucene version, and operating systems, kernel version, and even the memory options. Then we tested almost every combination in this table, but with hundreds of gigabytes of data for every test runs. It was very time-consuming, so we spent almost more than 6 months to completing all these tests. But our test failed except NVMe disk and also the local type disk. So we did not find the exact cause here, but our testing confirmed that this issue only occurs in the on the block storage. So we have to suspect several factors, such as issues with the file system caches, or the block storage might be the problem, or the Lucene has the bugs, but we haven't identified the root cause there. But fortunately, after some time passed since this test, we noticed that this problem occurred in only one of the 2 OpenStack regions where we served, and so we we start to compare 2 regions, focusing on the some disk options, and finally we find one option is different from the 2 regions. That is the disk cache modes. This hypervisor level option is used by the OpenStack Nova. Nova is the modules to managing the virtual machine, and it was set to write back in the region where the issue occurred. And the other region set to none. It means it does not use disk cache. And the write back option improves disk performance, but it has potential risk of data loss. That is the description of from the OpenStack. So as shown in this graph, the region A is with the write back settings, it regularly experienced the checksum failed error. This graph is the number of the checksum failed errors in 1 week. And whereas region B is you use non-settings, then it does not have any checksum errors. Even region B having 3 times more data than the region A. So we changed the disk cache modes to none for the OpenSearch nodes in some of OpenSearch nodes in the region A. So we changed the cache mode in region A. The checksum failed error is disappeared. As you can see the red arrow. So we apply on the 3 clusters. The OpenStack documents describe this option is safe on the block storage driver, but it can cause potential data inconsistencies in the OpenSearch. I don't know the exact reason, but I think that some cache miss maybe affect this, maybe make this happen. So we also test the performance between these options, write back versus none type. Because the write back use caches and it improves the disk performance, and disk performance is very important to the OpenSearch. So here is the result. the write-back mode performed better in single-threaded environment, but for the OpenSearch uses multi-thread read and write data when read and write. So there is no difference, almost no differences between these two options. So we decided to move from write-back option to none. Yeah, this issue troubled us for several months, almost over years, and even until this presentation was accepted, we had not identified the exact codes. So fortunately, we recently identified this option is the cause, and we can fix this. So I'm very glad to share this experience here today. So if you try to use network storage on your OpenSearch cluster, you might notice that this cache option can affect that kind of problems. Yeah, and the second issues I will share also related to the block storage, especially Ceph-based block storage. This time, the problem was not isolated to a single node, rather than the multiple OpenSearch clusters goes down at the same time. And nodes are evicted from the cluster with disk health check failed errors, and this issue also only occurred in Ceph storage. It is the block storage. The reason of these issues is critical. It affects multiple clusters simultaneously, so it not just happened on the single OpenSearch cluster. And with the multiple node failures, the primary and replication shards may both be lost at the same time. So it means that we cannot search that data until it recovered. And the third reason is OpenSearch attempt to recover data because the nodes are evicted. But in this situation, it makes a problem worse because it make another load and to the Ceph storage. Analyzing these issues, the Ceph distributes data as a block across the entire Ceph cluster. So this is beneficial under normal conditions for even if the load is evenly spreading across all the servers, all the Ceph servers. But problematic for a system like the OpenSearch with continuous read and write loads. When the OpenSearch load has been increased, it means that the connected storage, the Ceph storage load also increased, and then Ceph clusters, the response time is slower, and then at some point, the node health check from the OpenSearch, it fails. And then node evicted, and then OpenSearch try to recover missing shard, and it means that it makes another load, another shard movements, and it makes worse, and then it creates a cycle of repeated node failures. So to fix this, we manually adapted these settings to all of our clusters, almost over hundreds of clusters. We applied all these settings. It reduced network loads across the nodes, like index recovery, speed, or number of moving shards at the same time. Here is some points, the main cause of hashtag failed. The Ceph cluster load was not slightly higher than normal. It just a little bit higher than normal. And yet, and then but the OpenSearch determines the health check failed. We discovered this was due to OpenSearch's sensitive disk health check policies. And maybe you know the OpenSearch, if OpenSearch took over 5 seconds to disk health check, it determines that this disk is some warning status, and if disk health check took over 1 minute, it determines disk is failed, so the nodes are evicted. And then also, if 3 consecutive warnings, OpenSearch also determined this disk are failed to check health check. So the Ceph inherently involves some data access delays. So OpenSearch's sensitive health check settings were overly reactive in a Ceph environment. So this issue stemmed from the interaction between OpenSearch and Ceph. So we currently try to fix these issues, try to fix many of OpenSearch nodes goes down at simultaneously. So we haven't fully resolved these issues, but our experience highlight critical lessons. The OpenSearch's disk health check policies may not suit for the network storage environment. So I think that's why the OpenSearch installation guide does not recommend use network storage. And so if planning to use OpenSearch with network storage, consider adjusting this health check threshold, or if you need more Ceph storage resources for the stability, not just performance or some additional space. Yeah, I shared 2 representative issues we encountered with the network storage. However, it doesn't mean network storage is problematic or a negative choice with the OpenSearch. In fact, we've experienced clear benefits during our operations with the network storage. The first one is the reduced disk failure and server recovery times. Because the network storage have all their own data recovery strategies, so we don't worry about the disk failure, single disk failures, because network storage can recover itself, so we don't have to worry anymore. And then if computing nodes, I mean the virtual machine, if it fails, we can quickly recover by creating a new virtual machine, and instead of recovering entire data. That's very useful on the cold tier nodes. It can hold up to 10 terabytes in a single node. So if we configure this cold tier node with the local storage, we maybe it takes over an hour to recover, because there's quite a big amount of data. And then I mentioned before, the management burden for dedicated OpenSearch servers has been disappeared, because we use the virtual machine on our private cloud, and we have more than 100,000 of hypervisors for the virtual machines, and we don't worry about anymore the dedicated server fails. And that gives another advantages, because we when building large-scale clusters, we don't worry about the shard affinity. It has been collapsed. Yeah, so far I've introduced our OpenSearch service architecture and shared two major issues we experienced during operations. We plan to continuously expand our OpenSearch service. We expect our service grows over 10 petabytes in this year because many of users want to move their own clusters to the OpenSearch service. So I think we need some automated node maintenance policies, automated tools for the clusters, and also we have to prepare petabyte scale OpenSearch. Some users want to store their petabyte scale data into single clusters. So I know that there is some performance issues and stability issues in large scale clusters. So we have to prepare for that users. I hope the case I've shared today provide useful insight for or hints for those currently using or planning to implement OpenSearch service, especially with the network storage. And yeah, that's all I prepared for today. Thank you very much for your attention. Yeah, does anyone have questions? Yeah.
Yeah, thank you for an excellent presentation. So I think you mentioned this issue about the write-back cache and the problems that you were encountering with it. I think you solved it by setting it to essentially write through. That basically disables the cache completely, right? And also I think you mentioned that performance didn't change with that modification. So that's pretty interesting because it essentially is telling you that the cache is irrelevant, and that is rather strange. I think some kind of benchmarking with regard to the block storage and the utility of the cache would be very useful, because caches make a big difference with regard to disk and storage. So I think that's a very interesting observation that you came out over there. So that is one comment I wanted to make. The other thing with regard to Ceph, I think you have this Ceph storage across multiple clusters. And one point that you might want to look at is to have separate Ceph implementations per cluster so that problems in one cluster don't emanate to the other clusters, right? So that is one change that you could do. And also the 5-second health metric with regard to the health check is pretty reasonable, I would think. I mean, for Ceph not to respond within 5 seconds is rather strange, as far as I can see.
Yeah, thanks for your advice. And we also try to find the root cause, and I think the increasing the health check threshold is not the solutions. Yeah, so we maybe find some solutions for that, and then I want to present once more. Yeah. Thank you.
Yeah, sounds good. Thank you.
Yeah. And there's one.
Yeah, thank you for your presentation. I find the scale where you're moving is really, really interesting. I was wondering what kind of automation you're using to keeping your configuration consistent and setting up new clusters. So what level of automation you're currently moving in, and maybe what kind of automation you're looking to implement?
Yeah, we based on the Kubernetes controllers that I mentioned earlier. we made our own Kubernetes operator to deploy and managing our OpenSearch clusters, but we not rely on the official Kubernetes OpenSearch operators because we deploy our OpenSearch nodes on the OpenStack. So we basically relies on that controllers, that operators. Yeah. So maybe most of the automated features implemented with operator patterns. Yeah. But some other automated features like update setting and sync settings, and that is relies on some other Kubernetes modules, such as the jobs or batch jobs. Yeah. Yes. Yeah, that's it. So we try to make it better, but on the Kubernetes. Yeah. Is that enough answer? Yeah. Thank you very much. And there is no questions anymore. Then that's it. Thank you for attending my sessions.